So we're going to look at troubleshooting PLCs, the presentation. This is the instructions. I think we've all been through this. As I say, I apologize, Carol can't make it. She's got an ear infection. She's not very good at getting it up. I will make sure, I promise you, that you'll get a copy of the recording, the PowerPoint slides, and there's a few extra bits of information I want to get. We did do this presentation a few months ago, but Carol felt that we needed to run it again. Every few weeks we do a quick interactive course. Hopefully it's some use to you guys. Try and be as quick and useful as possible. Obviously what makes it more interesting is we have interaction from you guys. Hi Tom, Darlington, Dennis, Emmanuel, Gavin, Hervé, I can't pronounce your name properly, James, Mohammed, Jabulo, Percy, Sharon, and me, Mackay, and Tim. So, get you out there, Tim. What we want to try and do in this little section is just briefly look at some typical problems with PLCs, look at troubleshooting software, and then identify some of the actual issues related to PLCs, which of course is my favorite topic, which is good old industrial communications. So topics that we're going to cover very quickly: introduction to PLC, internal, external problems, internal problems in a bit of detail, external problems, applications, conclusion. Can you tell me, first question is, can you all hear me? And if you can hear me, please give me a smiley little face. I just want to make sure there's no dropouts or any nonsense like that. So please just confirm you're happy. Yep, thanks, Sharon. I'm delighted you can hear me. Everyone else, can you hear me? Please give me a little. Thanks, Tim. No one? Okay, James, Gavin. Yeah, I like the sunglasses. Gav, if you know last night, Darlington. No one else. Okay, fair enough. Okay, thanks, guys. Can anyone tell me, next question, some dropouts. Okay, I'm sorry about that, Dennis. If anyone has dropouts, please let me know. I'll be interested to know. Maybe my internet here. Can anyone tell me what is the most likely problem you have with the PLC? Internal faults or external problems? In other words, external lines, in your experience. What is the most common problem? Yeah, thanks very much. Gav, absolutely right. External is the number one problem, absolutely. Now let's just have a quick look at what we're talking about there. I think it's about 70%. So before we go any further, obviously we're looking at this in the context of industrial automation skills are extremely useful, and you should be able to troubleshoot, identify, fix PLC and SCADA problems. So if you are a graduate engineer or an electrician, anyone working in the automation business, one of the biggest needs for you is able to troubleshoot and fix problems. So obviously PLC, which could be internal, external problems, and obviously SCADA problems. Obviously not asking to rewrite the SCADA package, but you should be able to say, I think we have a Ethernet problem with this particular CPU or RTU connecting to the SCADA. Let's have a look at what the problem is. Let me put the protocol on. So quickly diagnose and identify what the problem is. So let's have a quick look at what the PLC is, and then I'm going to obviously look at some of the internal and external problems. As you guys rightly point out, problem number one is the good old PLC is normally fairly happy. But before we go any further, let's quickly summarize what the PLC is. Is anyone there that can take over the microphone and tell us what the PLC is? Anyone who can take over the microphone, please? You've got a 10-second soundbite to tell us what the PLC is in 3 sentences. Over to you guys. Darlington, Tim, Sharon, what's a PLC in a few words? Please talk. Please, please. If anyone has any suggestions, text it and, thanks, Gav. Over to you, Gav. I didn't hear you, Gav, but if you want to take the microphone again, please shout. Essentially, there's a few words here about PLC, but probably the best diagram is a little diagram here. This is a really great little diagram of PLC. I will go back to the text. If anyone wants to add in here, basically what we've got on your processor is a little program running, generally ladder logic, which you guys are familiar with. Ladder logic program, and contacts and coils. And the idea is that this has what we call a scan cycle. So the scan cycle basically starts with read all your analog and inputs, external, read them all in from inputs. That's the beginning of the scan. Then execute the ladder logic program. And at the end of the scan, output to your relays, valves, digital outputs, or whatever. So that's the thing. And then again, the beginning of the scan starts again, and then you start up with, oh, great, Arch, I'm sorry about all the problems there. And then once you've done the scan, you execute and read the inputs again. Now the question for you guys is, can anyone tell me typically what a scan is in milliseconds? What's a typical scan time? What is the typical scan time? Yep, thanks, Archon. Oh, thanks, you very quick there. 20 milliseconds. Yeah, look, I mean, if you're between 5 and 20 milliseconds, you'll be probably pretty average. If you are an older PLC programmer, you may be talking about 70, 80 milliseconds because you had a whole lot of PID logic or something else, or a few thousand runs of code and a very slow scanning PLC. But typically today, yeah, I mean 10, 15 milliseconds, very quick. Why can you not have a long scan time, say 80 milliseconds on a PLC? What would happen if you had an 80 millisecond scan on a PLC? And by the way, 20 years ago, I did have a PLC like that, and it caused enormous pressure. Yeah, thanks very much, Tim. As Tim says, if you had a quick change of state, input goes on, a little contact goes on and then off again, it may happen within that 80 milliseconds, so of course you miss it. Obviously, you've got to keep your scan as close, as short as possible. There are ways around that problem, but generally you want to keep your scan quick. Okay. So that's the basis of the PLC. What makes a PLC such an incredible animal? Well, it's industrial, it's robust, and don't take me the wrong way, but an orangutan can program it. Obviously, an orangutan can't design the program and make it readable, but it's very straightforward to program. It does require a lot of thought and skill to actually put together a good program which is coherent and readable. There's no doubt about that. But this presentation is not about programming. So that's what a PLC is. And there are also other animals that are around now called PACs. Again, the marketplace is always looking for differentiation. So if you have a PLC which does perhaps basic programming, stronger from National Instruments, you'll probably find that we call it a program or automation controller. And PLCs, as I said earlier on, are digital animals, but of course analog is very strong today as well. PID control used to be very painful, but effectively as well. But the great thing about a PLC is simple to program, you can buy them off the shelf, and very easy to set up and run. So very, very important. Other little problems with the PLC, which we haven't really indicated in this diagram, of course, are power, electrical power issues, power coming in. And this is the working of the PLC CPU, the scan time, as you guys rightly pointed out, 2 milliseconds, 30 milliseconds. The scan starts off with read, execute the program, write. Do all that in 10 milliseconds. There's a few other tasks here as well, of course, which we haven't really spoken about, which can also confuse things, which can be a little bit of a challenge. Sometimes you have what they call asynchronous communications. In other words, you're bringing in values from other I/O racks, and they may not arrive. They may arrive at different times during the scan, so that may also cause a bit of issues. But most of the time, it's pretty quick communication. Ladder diagram is an example of ladder diagram. Can anyone tell me how this operates here? Anyone can take over the microphone. Tim, have you got a microphone there? Can you explain this little rung of logic to us here? Gav, can you talk? Oh, Tim, can you take the microphone? Let's have Tim. Let's hear someone else besides boring Stevie boy. Let's see who gets the microphone. It's either Tim or Gavin. Question is, please explain that rung of logic there. Over to you, Tim. Over to you.
Yeah, from the start we've got a normally open start, push to start obviously, then we've got a stop switch which is normally closed, which then runs the motor, and you've got to hold on cable below it. Is that right?
Absolutely fantastic, Tim. Thank you very, very much. As Tim rightly pointed out, he made a few very important points there. You've got maybe a push button start, closes that, your power flows through. This is also normally closed, so you get power flow through there, and you energize the contactor, and on the next scan through, you'll find that this will then be sealed in, or latched in as they say, and you then have it continuously on. If there is an emergency, and let's change the color here, as Tim pointed out, you have emergency stop button, you push the stop, this will then break the power flow and of course stop it out. Obviously, very, very important, according to state legislation, and most reasonably well-established governments around the world will make sure that it's all hardwired. So, emergency stop button, I've got my hand in the conveyor belt, I pull the pull wire, it trips it out, whatever the programmer has done. So obviously very important that this is fail-safe, and it's external to the PLC as well. So that's not an issue. Okay, so that's just a quick bit of logic there which is running. And here's a sort of typical example of the power flow. Jim has explained it more adequately. Now, internal, external problems. As you rightly pointed out, the programmer isn't generally the problem. It is your external situation that is the problem. That's what obviously we're going to watch out for. So about 80% of malfunctions, and this is from a reputable American magazine, I reckon 80% are to do with I/O modules. So you can assume that most of the time your problems with the PLC relate to something outside the PLC. Everyone instinctively looks at the PLC as a black box and immediately thinks there must be something wrong with the PLC, especially a guy who hasn't worked with the PLC. Look at it and say, and that's one of the major problems, I think, is whenever you set up a PLC system, you have to make sure your program works smoothly and the system has predictable problems, or you can identify them very quickly. There's nothing that drives a client into a catatonic state than finding out what the hell is going on with this PLC system as far as controlling the plant and all the problems it has. If you have large groups of failures, like a whole lot of I/O fail, well, very rarely, and hopefully you flying a plane in the cockpit of your jumbo plane, you don't suddenly discover that all the lights are flashing on and the CPU's failed. Well, you may have an internal failure in the PLC, but this is very, very unusual, very unusual. I've only had it in my 25, 30 years of programming PLCs. I've only had 2 or 3 situations where there's been some failure, a whole car internal failed, or had a CPU firmware problem. And admittedly, when the problems occurred, they were major. One problem that really comes to mind, which was caused by the fact that if you look at that picture of me now, I've got grey hair, white hair. So forgive me, some of you guys heard the story before, but I was testing a Rockwell system, and there's no one from Adam Bradley here, but testing a Rockwell system in the middle of the great outback for a power station, gas turbine station, and we were testing hot standby. Power stations went on standby. Inevitably, we did the changeover to the secondary CPU, the Adam Bradley PLC, and all the analog values froze, the whole lot. It was a then we had massive failure, and it was an absolute disaster. And I mean, the Americans come along and say, well, don't worry, Steve, you know, anything you buy from us, it would have been installed on many, many sites around the world. Well, not really the case. Whenever you buy hardware, software, always you may be the first recipient. Anyway, 80% of malfunctions are generally the IR. That's what you're going to look for. So let's have a look at internal problems before we go any further. Internal problems to the PLC are earthing, grounding is correct. Has anyone here had problems with earthing, grounding PLCs? Any challenges there, guys? Gav, over to you. Any problems with grounding, earthing PLCs? Over to you.
Yeah, mainly with communication links, so we don't use a lot of analogs, but we have lots of problems in high voltage substations with circulating earths or that type of thing.
Thanks, Gav. Yeah, very good point. I didn't mention it there. Gav says, and perhaps Gav, you can raise your microphone volume a little bit. But as Gavin says, yeah, one of the challenges, earthing, grounding, which is particularly malevolent, particularly nasty, communication links. And I'll come back to that a bit later. But comms links, believe me, earthing, grounding is a major issue. You should always, and I've learned the bitter hard way, try and use RS-485, but even RS-485, which is a really great communication standard, you can actually have subtle problems with common mode voltage, which means that your remote racks drift up in voltage and you have a problem. So really, at the end of the day, the best way to get rid of all your problems with common links is try and use fiber if you can. But certainly, a problem that you can often have is the PLC manufacturer goes to a great length to tell you about earthing or grounding or chassis. Please make sure that's done properly and your overall earthing plan is good, because you will find often this is the cause of very strange, unexplained problems. And the problems are with earthing is that it doesn't just happen and you have an outright failure. You have an intermittent fault and then you don't know what the hell's going on. You find your remote rack drops out intermittently, you reset it and it's all running okay. Well, believe me, it'll come back again. That seawater pump will drop out again. Check the power supply of the PLCs within the correct range, not excessive. Batteries in the PLC, that's a fairly standard problem. Make sure that, again, that doesn't happen until your battery fails. Very rare that happens. The PLC program has been corrupted. It happened to be once with a brand of PLCs which will remain nameless, where the actual program was corrupted. The spike went through and it corrupted the CPU. Again, very unusual. And you'll find most PLCs you can actually look at internal diagnostics. I honestly say that I often find that people don't use the internal diagnostics of the PLC enough to actually identify problems. And it's really it's probably because in most cases internal diagnostics are very difficult to get your finger on exactly what the problem is or how to use them, if they will think. Percy says, what would be the cause of frequent battery failure? Yeah, look, battery failure in the context of the PLC, Percy, is just really a backup battery for your memory of your PLC. So after 3 years, battery stuffed, and of course, bang, you've got a problem. But as I said, very unusual. Happens. What normally happens at that point, which happened to me on a mineral sands plant, the battery failed, and they had a power failure to the plant at the remote site, and they knew immediately the battery failed, because when they boosted up the PLC again, there was no program. And of course, inevitably, someone had been making changes to the program for the last 3 years since I've been on site, and of course, we got an anguished call from the client, please can you give me the program? And of course, we didn't have to change it. We gave them what we had, but it was 3 years out of date, so it didn't help them much. But, they should have backed up. External problems, obviously, are the interesting ones, and as I said, we discussed that's probably where most of your killer problems come from. External problems, digital inputs, check the power supply to the module. It was a particularly incredible problem with Argyle diamonds. Very interesting problem, actually. And again, I would say most of you guys probably would have been well outside your vintage, but it was just as I was working in Western Australia 24 years ago, actually 23 years ago, particular problem with a particular PLC brand there. Their batteries, in fact, firstly it was to do with batteries. Batteries were connected up on the plant, and they were connected up in series, so you had 48 volts. The modules of the PLC were sized for 48 volts, so there was no problem at all. But they weren't sized for 50 volts or above. So it was 48 volts modules, and the batteries, when they were fully charged, lead acid would actually go well beyond that. So the digital inputs were always failing, and they had thousands and thousands of inputs. But that was a problem in the history of things. So just when you check your power supply and your power inputs, just make sure that they are within the range of the inputs. So just bear in mind you will get a range of the voltage, fluctuation of voltage, and you need to be aware to check fuses and breakers. And if your digital inputs are fine, check that the light comes on your module. Well, you may find that the programming problem. So with inputs, always another good thing with inputs. Can anyone tell me what you should think about with input cards if you can? Any suggestions? Input cards for your PLC, guys? I'm sure Gav or Tim have a few comments there. Any comments there? What do you notice about these modules here? Which make them quite useful. Tim, do you want to take the microphone? We can hear your dulcet tones rather than my boring natural accent. Yeah, thanks, Gav. As Gav says, probably a good, still living, Tim. I think, Tim, you know probably more than I do. But as Gavin says, yeah, one of the good things here with this particular module, and a lot of modules aren't this way, but is you've got optical isolation. Can you see if you have a spike coming through here? Bang. The spike actually doesn't go into your guts of your PLC. So basically what's happening here, you've got a nice isolated input. If you can go for inputs which are optically isolated, you do save yourself a little bit of stress in the long term. It costs a bit more. Most high quality inputs do have some sort of optical isolation, but this immediately isolates you from any spikes. That's always a good idea. Digital outputs. One other problem here, actually. One other problem, which very, very subtle problem, actually. I'll be running out of time here, but one problem that caught me. I don't know if any of you guys have used these proximity detectors. I had a particular problem once where the proximity detector had sufficient leakage current going through it, so it's one of the devices here, to keep the input on when the proximity detector was off. There was nothing near it. And it was a tricky problem, actually, and it was quite difficult to fix because we had a lot of these little proximity detectors, and they had sufficient leakage current to bias the inputs on. So input should be off, and I saw it as off but, from the proximity detector, but there was sufficient leakage current within the legs of the PLC to say, hey, I'm still on, brother. And it's actually off. So just those are tricky little problems, leakage currents. Mainly poor quality manufacturers. Digital outputs, obviously power supply. Make sure that control fuses, your outputs. Make sure that they haven't blown. Force digital outputs on and off. That's a quick way to see what's going on, but obviously make sure you remove the forces eventually. And test load rather than open circuit to test your outputs. Why do we make this comment here? Can anyone tell me? Why should we use a test load rather than open circuit to check whether the outputs are on or off? Any suggestions? Anyone besides Gav or Tim? Hello? I'm passing a microphone to someone, or just text it there. Why would you use a test load rather than open circuit? Any suggestions when you're testing the digital outputs, guys? I'm going to leave the microphone, hand it over to anyone who wants to grab it. No comments. Okay. Yeah, look, Tim, you make a good point. Obviously, you could have a particular situation where you have outputs which you don't want to start up. I mean, you could be switching on a ball mill, for example, 1 megawatt of brute power. So you may want to think. But no, the point I'm making is that you can often see the outputs go on when you force them, but the real tester, if you're providing current or anything, is just to check that the output can actually deliver the current, the power that you want. Watch out for that. And just a few other little comments here, just a few throwaway comments actually. Yeah, the output module is again, so you can. Just bear in mind also that if you're dealing with digital outputs and things like that, they may all be, each channel on your output may be rated for a particular amperage, like 1 amp, but you may find that, and you may have 8 output channels and each one's 1 amp, but you may find that the overall module is only rated for 3 or 4 amps, which means that you can't deliver all of them on at the same time because you have a problem there. So make sure that you know the total load required for your system and whether your output module can supply that load. Maybe just one thing, it may be too much dissipation of heat that fails. Analog inputs, yeah, move the field device to the full range of currents. I've had a particular problem where the A to D converter actually partially failed and we had some problems with some part of the range. Signal transmitter is the best way to be absolutely sure what's going on. Go through the whole range. On analog outputs, best thing is force the output to specific value and check, and also check your external wiring. One other little challenge with these inputs, if you've got problems, and it's beyond the scope of this presentation, but the topic which has caused me to have grey hairs, I was trying to tune, in fact, it was quite a funny problem actually. I was trying to tune a loop, PLC loop, PID loop. So you take your analog inputs, apply your PID algorithm, which is proportional integral, simple flow loop, and then you drive the output. And I couldn't tune the loop. I couldn't get the loop tuned. And I battled. I checked the PID parameters, did everything. And basically, what I was reading with my analog input was rubbish, absolute rubbish. Can anyone tell me what was happening with my analog input? Any suggestions? Anyone can guess. It was extremely painful because it took me a few days to work out what was going on. And in this case, I actually drew on my mainly useless university theoretical background to work out what the problem was. Any suggestions what the problem was? I wasn't reading the analog value correctly. Can anyone tell me why? What was happening? I'll give you a clue, guys. We also had set up a whole lot of variable speed drives and they were all running. Yes, thank you very much, James. Absolutely right. What was happening was, and this is a really, really tricky problem, and it really caused me to really scratch my head. What was happening was the variable speed drives were creating harmonics. My initial reaction was there was electrical noise getting into the cable. So it was coming into the cable, and the power cables are running, they're about half a meter away from the 4 to 20 milliamp cables. I thought, it must be noise getting in from the power cables. But no, it wasn't that at all. It wasn't that at all. What was happening was I was running a little, you could call it a little radio station in that MCC, motor control center, and we had harmonics all over the place, and they were coming through the earth, and they were everywhere, harmonics in these variable speed drives. And what was happening was I had all these harmonics on my normal signal there, and they were all sorts of high frequency harmonics. And I had what we call an aliasing problem. Aliasing. Basically, it means that my sampling rate because of the harmonics, I wasn't sampling the analogs at the right speed. Now, obviously, you're not designing to sample your analog signal at 10 kilohertz or 100 kilohertz, which is what a lot of these harmonics all over the place. So what we had to do was, and so basically what it was doing, aliasing, which meant that I wasn't sampling at the right rate, PLC input card, and of course I wasn't reading the right analog value, and I was doing my PID calculation on the wrong analog value because I was reading rubbish. The only way to fix it was putting signal conditioning in. We put signal conditioning in for about 30 or 40 analog inputs. That was a nightmare. But once you put signal conditioning in, bingo, problem solved. That's an issue with software. Okay, applications. A few other applications here, remote troubleshooting. Just a few little problems. Remote troubleshooting, watch out for network security, hackers about 24/7. If you're ever troubleshooting remotely, and we've been troubleshooting remotely for 30 years now, guys like Honeywell have been logging into systems with modems, not through the internet, 25 years ago, logging in and making changes. But today, with the internet, it's a lot easier to get into a system. Transients, as Gavin mentioned early on, transients are a real problem. Fiber optics where possible, good earthing for your datacom systems, but also try and use fiber optics. Fiber optics gives you two solutions. One is no noise, because you can't get noise in a fiber system, no noise. And the other great thing is no spikes, transients. Quite a good system. So no electrical noise, so not copper, and no spikes. So two good points. Physical shield here. Little thing here, which obviously the idea is you only earth at one point only. Watch out you don't have, which I saw on one Alcoa site many years ago, intermittent earth along here. Obviously, intermittent earth on your shield means that you've got multiple points, which again is a problem. For those of you that are super gurus in the class, in the group here now, you can actually earth a screen of multiple points with capacitive coupling. But to be honest with you, very rarely do you see applications like that. And for all intents and purposes of this presentation, earth at one point only, but watch out for intermittent earth because your screen is making contact with multiple points. That's to eliminate capacitive coupling. And as we said, always watch out for transients, put in some sort of optical isolation using copper cable. And then when in doubt, disconnect. Yeah, I think I've told you this story many times. Forgive me, Gavin and Tim and Dennis, if I've told you the story, but it will always remain in my mind, my demented mind. We had a PLC programmer, straight out of the university, graduate engineer, top of the class, gold medals, the whole thing. Anyway, he was programming the PLCs for us because we needed cheap labor and graduates were cheap. Client had no money, programming it. But the graduate didn't know the difference between a 1 megawatt ball mill and a 100-watt grease pump for the ball mill. As far as he was concerned, it's just a number of a contact. So when the client was, our Japanese clients have been shown around the plant, and then our client said, look, I'll tell you what, I can't start the ball mill up, but I'm just going to just show you the grease pump. I'm just going to push the button on the grease pump and that'll start it up. But he pushed the button and of course we had the ball mill start up at that point. So obviously major confusion. So if you've got any doubts about switching on pointers, make sure you check it out. But one point here again is make sure if you're doing any controlled analogs or digital outputs, make sure that you do give them a load due to them to check your cards, your analog digital output cards. Okay, that brings us to the end of the presentation. I'm sorry if I've overstayed my welcome a little bit here. That sort of thing. I will make sure that you all get copies of the presentation. And there's a few extra, there's a chapter extra which I'll send to you as well on troubleshooting, which you may find useful. I just want to give my very warm thanks to Tim and Gavin and Archom and the other guys that contributed here, and also naturally thanks very much Darlington, Dennis, Emmanuel, Izina, Gav, Hervé, sorry if I've mispronounced your name, James, Mohammed, Najabalo, please forgive my pronunciation, Nuruslam, Percy, Sharon for coming along to this presentation. Actually, Tim, thank you very much. As I said, if you don't get it by tomorrow, but you should by Friday, you'll get the recording, the PowerPoints, and there's some additional notes that I'll send out. If you have any other comments, please shout. Thanks, Sharon. Thank you very, very much for coming along. Thank you for pitching up. The next presentation, we're going to liven up with more programs running on the PC as well. Now, this program is pretty bulletproof. Thank you very much. Thank you. And to log out, just click on File and then exit out your. Thanks very much. Any questions? Just any questions? Just send any questions or comments. Just send them to steve.mackay@. Thanks very much, guys. Much obliged. Sorry, Zina, I was just on something else, another call. You'll get the material sent to you, Zina, tomorrow, or Friday at the latest. You get all the material sent to you by Alison or maybe Rachel, but one of them will send it to you. They've got 200 people to send it out to,